a place where you never get harmed. A magical place with magical charms. Indoors, indoors, indoors.
If only they were actually true given the current situation that we are in. How's it going, guys? I'm dyslexic, it's kicking in. This is Mike coming at you with another video on vector calculus. In the previous video, we talked about the integral of a vector field across a surface, capital S. We saw the formula, we compared it to the integral of a vector field over a curve. We talked about orientation of surfaces, and we found that what this idea is, the idea of the integral of a vector field over a surface S is really just the flux of our vector field across our surface. In this video, we're going to go through some sample problems to see how do we use that formula to calculate the flux of some vector fields across some surfaces. We're going to move on to the next sample here. Again, we're going to find the flux. In this case, our vector field, capital F hat, is 2x, comma, minus 2y, comma, z squared minus the tangent of the natural log of x. And S is the portion of the cylinder of radius 3 and height 5 that lies in octants 1 and 2. Now, as we mentioned in a previous video, unless specified inside the question, you can assume that the base of your cylinder lies in the xy plane. First thing we need is the parameterization for our cylinder. This is one of those basic friendly shapes that you need to know how to come up with the parametric equations for it. Your parameterization, capital phi hat, is 3 times the cosine of u, comma 3 times the sine of u, comma v. V is what controls our height. So we said that our cylinder has height 5, so v is going to go from 0 to 5. Now u controls how far we go around in a circle, specifically in our circle that has radius 3. Now the problem specified that we're working with the portion of the cylinder that lies in octants 1 and 2. Octants 1 and 2 correspond to quadrants 1 and 2 in the xy plane, so we need the angles that sweep out quadrants 1 and 2, and those angles are from 0 to pi. So my bounds for the variable u here are going to go from 0 to pi. Just like the previous problem, we need to find those tangent vectors, t sub u hat and t sub v hat. Again, pretty straightforward here to calculate, just using basic calculus 1 derivatives. We get negative 3 sine u, 3 cosine of u, 0, and then for t sub v hat, we get 0, 0, 1. Take the cross product of these two guys, and we get 3 cosine u, 3 sine u, 0. I need to take my parameterization and plug it into my vector field, capital F hat. And when you do that, you get 6 cosine u, comma, negative 6 sine u, comma, v squared minus the tangent of the natural log of 3 times the cosine of u. Now, looking at that z component of your vector field, you think, oh my god, how am I going to take the integral of that ugly looking thing? I wouldn't even know where to start. Well, keep in mind that we're taking the dot product of this vector and our cross product vector. And if we take a look at the z component of our cross product vector, we get 0. So thank God we do not have to worry about this guy here. So that dot product is going to become the integrand in our double integral. If you take the dot product of capital F hat and our cross product vector, we get 18 cosine squared u minus 18 sine squared u dv du. Now, if we pull the common factor of 18 out, we're obviously left with cosine squared u minus sine squared u. And we can use a trig identity. Cosine squared u minus sine squared u is simply the cosine of 2u. So, we have the double integral from 0 to pi and from 0 to 5 of 18 times the cosine of 2u du. Integrate with respect to v first. There is no v showing up in there, so this guy is just a constant in the eyes of this inside integral. The integral of a constant over an interval is simply equal to the constant times the length of the interval. So that's just going to give us 90 times the cosine of 2u when we do our inside integral with respect to v. So we're left with the integral from 0 to pi of 90 times the cosine of 2u. This is a very low-level u substitution. You should find that you get 45 times the sine of 2u. Take your top bound of pi, plug it in, we get 0. Take your bottom bound of 0, plug it in, we get 0. So we come up with our most favorite answer in the entire world, 0. I just want to make one more quick note here about our surface and the normal vector. We said that for any one of our nicer shapes, like a sphere or a cylinder or an ellipsoid or a cone, we're going to be working with the outward pointing unit normal. If you picture a cylinder and you picture an outward pointing vector that is normal to your surface, that vector is going to be parallel to the xy plane. So there is no z component. That z component is just 0. So that's why we see that we get 0 in the third component of our cross product vector up here at the top of our screen. Also, since we're working in octants 1 and 2, which correspond to quadrants 1 and 2, as we said, in quadrants 1 and 2, we have a positive y value. So we see that we have 3 times the sine of u as our y component of our cross product vector. And for u going between 0 and pi, sine of u is positive. So this normal vector here does indeed make sense. On to the third and final problem that we're going to look at. Again, we're going to find the flux, but this one's going to be a little bit more complicated. There's going to be a little bit more work that we have to do here. Vector field f hat is 3x comma 2z comma 1 minus y squared, and our surface here is the portion of 2 minus 3y plus x squared that lies above the triangle in the plane with vertices at 0, 0, 2, 0, and 2 comma negative 4. We'll see that for the most part, this is going to be the same method, the same number of steps, but we need to do a little bit more work when finding out our bounds. So first thing, as always, we need the parameterization for our surface here. Again, this is a function of 2 variables, so the parameterization is nice and easy and straightforward. U comma v comma 2 minus 3v plus u squared. But here's where the extra bit of work comes in as far as finding our bounds. We need the triangle in the plane with vertices at 0, 0, 2, 0, and 2 comma negative 4. You can see that I've sketched the x and y axes here on the left-hand side of your screen, and I sketched that triangle out. We need the equation of the line that's forming that hypotenuse of our triangle, and that line you can find with very little trouble. You can find that the equation for that line is y is equal to minus 2x. So we're going to use this red region, we are going to come up with our bounds for u and v from this red region here. We find that for any point in this red triangle, that as the x-coordinates or the u-coordinates, since u is equal to x, as the u-coordinates go from 0 to 2, the v-coordinates, again, v just took the place of y, the v-coordinates start at minus 2u, and they go up to the x or the u axis. So v goes from negative 2u up to 0. So these are the bounds that we're going to need to use when we calculate our double integral. So you have to be very careful about what the question is specifying as far as what your surface is. Now we go back to our typical routine process. We're going to find the partials of our parameterization with respect to u and v. Again, pretty basic, pretty straightforward. We get 1, 0, 2u, and 0, 1, negative 3. Take the cross product of these vectors, and we are going to get 2u, comma, negative 3, comma 1. I need to take my parameterization and plug it into my vector field. When you do that, you get 3u, comma, 4 minus 6v plus 2u squared, and then comma 1 minus v squared. We take the dot product of our vector field and our cross product vector. That gets us our integrand in our double integral. And we find that we can cancel things out, combine some things, and we're left with the double integral. U goes from 0 to 2, v goes from negative 2u to 0 of 18v minus v squared minus 11. We're going to integrate with respect to v first, and we have to because if we try to integrate with respect to u first and then v, we're going to get an answer left in terms of u's, and that's not what we want. Integral with respect to v, pretty straightforward. Take your top bound of 0, plug it in, you get 0. Take your bottom bound of negative 2u and plug it in, and we get 36u squared plus 8/3 u cubed plus 22u. Now it's 0 minus that thing, so that's why we have the minus in front. That's why we have minus that whole quantity. So we're going to take the integral of this guy with respect to u. Again, down to a basic Calc 1 type of problem here. Nothing crazy happening. Integral is 12u cubed plus 2/3 u to the 4th plus 11u squared. Take your top bound of 2, plug it in, you get 452 over 3. Take your bottom bound of 0, plug it in, you get 0. So our final answer is negative 452 divided by 3. Again, the only new part to these problems should really just be coming up with the parameterization, finding the tangent vectors, finding the cross products, taking your parameterization and substituting into your vector field, and then taking the dot product of those two things. But even most of that is not necessarily a brand new concept to us. For the most part, it's just that formula. So these were some practice problems on finding flux of a 3-dimensional vector field across a 3-dimensional surface. In the next video, we are going to reflect back on Green's theorem, specifically the circulation curl form of Green's theorem, and we are going to basically see what does that thing look like when we scale it up into R3. and there's a special name for this theorem, but we will reveal that in the next video. If you guys have any questions or comments, be sure to drop them in the comment box below. Otherwise, until the next video, guys, take it easy.